In this video, we extend the state space conversion method to a system with more than one coordinate. Here is a simple 2 degree of freedom mass spring system where the two displacement coordinates are q1 and q2. Instead of one second order ODE, we now have two coupled second order ODEs. The first equation describes the force balance for mass 1, and the second equation describes the force balance for mass 2. The equations are coupled because q1 appears in the second equation and q2 appears in the first equation. This coupling comes from the spring between the two masses. Before we write the system in matrix form, it is worth noticing that we have two coordinates and two second order ODEs. The two scalar equations from the previous slide can be collected into matrix form. For this example, the mass matrix M is diagonal. The first acceleration is multiplied by m1, and the second acceleration is multiplied by m2. The stiffness matrix K contains the spring connections. The diagonal entries collect the springs attached to each mass. For mass 1, that gives K1 plus K2. For mass 2, that gives K2 plus K3. The off-diagonal entries represent the coupling between the two coordinates. With both displacements measured positive to the right, the spring connecting the two masses appears as minus K2 in both off-diagonal entries. The same pattern extends to larger mass spring systems. Diagonal entries collect stiffnesses attached to each coordinate, while off-diagonal entries describe coupling between coordinates. So the two coupled scalar equations can be written compactly as mq double dot plus kq equals 0, where q is the vector containing q1 and q2. Now that we have the compact matrix equation mq double dot plus kq equals 0, we can rearrange it to q double dot equals minus m inverse kq. This can look a bit like a state space equation, but the left-hand side is still q double dot, so the equation is still second order. A state space model is a system of first order ODEs. The vector q contains the two displacement coordinates, q1 and q2. But for this second order mechanical system, the first order state vector also needs the velocities. So q has two entries, but the equation is still second order. We still need to choose a state vector that turns the second order vector equation into a first order state space system. Since the matrix equation is still second order, the next step is to choose a state vector that lets us write a first order system. For this second order mechanical system, a standard choice is to include the displacement vector q and the velocity vector q dot. So we define x by stacking q and q dot, where q contains q1 and q2, and q dot contains q1 dot and q2 dot. Equivalently, if we label the entries of x individually, then x1 equals q1, x2 equals q2, x3 equals q1 dot, and x4 equals q2 dot. This gives the state count for this example. A 2 degree of freedom system gives 4 states because each coordinate contributes a displacement and a velocity. Now we follow the same process as for converting a single ODE to state space form, but this time with vectors. Since we defined x by stacking q and q dot, differentiating x gives q dot in the first part and q double dot in the second part. From the equation of motion, the acceleration vector is q double dot equals m inverse kq, which we substitute into the lower part of x dot. The block matrix A is a compact way to write the full 4x4 state space matrix. The top block row gives q dot and the bottom block row gives minus m inverse kq. So the coupled second order system has now been rewritten as a first order state space model x dot equals ax. There is one state ordering point worth making here. In this video, we stack the displacement vector first and the velocity vector second. So x contains q1, q2, q1 dot, and q2 dot. With this ordering, the A matrix has the block form shown here. This ordering is convenient when we want to write the system compactly using q and q dot. Some books or courses use a different ordering. For example, they might pair each coordinate with its velocity, q1, q1 dot, q2, q2 dot. This ordering is also correct, and it can be convenient when we want to keep each degree of freedom together. The physical system is the same, but the A matrix looks different because the state variables are ordered differently. The important point is that the A matrix has to match the ordering of the state vector. We can also include damping and inputs in the same framework. With damping and an input vector u, the equation of motion becomes mq double dot plus cq dot plus kq equals u. For this example, we are allowing one input force for each coordinate, so u has two entries, u1 and u2. When we isolate q double dot, the acceleration has three parts. The stiffness term gives m inverse kq, the damping term gives m inverse cq dot, and the input term gives m inverse u. Using the same state vector as before, x is made by stacking q and q dot, so the state space model now has the form x dot equals ax plus bu. The damping term changes the A matrix by adding the m inverse C block. The input term gives the B matrix, with m inverse in the lower block. For this example, x has 4 entries and u has 2 entries, so B is a 4x2 matrix. In general, B has one row for each state equation and one column for each input. So damping and these external inputs change the matrices, but they do not change the number of states. Before we state the general rule, let's look at one mixed order example. Suppose one coordinate is governed by a second order equation and another coordinate is governed by a third order equation. The exact functions on the right hand side are not important here. The main point is the order of each coordinate. The first coordinate contributes 2 states, q1 and q1 dot. The second coordinate contributes 3 states, q2, q2 dot and q2 double dot. So the total number of states is 2 plus 3, which gives 5 states. Now let's summarize the general state counting rule. State variables count the first order variables needed to describe how the system evolves. So the number of states depends on both the number of dynamic variables and the order of the equation for each variable. A useful rule is total states equals the sum of the orders of the dynamic variables. For a standard second order mechanical system, the dynamic variables are usually mechanical coordinates, such as displacement or angles. Since each coordinate is second order, each coordinate contributes 2 states, the coordinate itself and its derivative. Therefore, a standard n degree of freedom second order mechanical system has 2 n states. For example, a 3 degree of freedom system has 6 states, and a 4 degree of freedom system has 8 states.